Hello dear students, I am back with another session of physics, and already I have taken one session of potential and potential energy, and we are continuing from there. I hope you have seen that video already on potential and potential energy, because we are continuing from there. And still, if you haven't seen that video, then I would advise you to first go through that video of potential and potential energy, so that entire context is clear to you. Today we are going to take two important points. One is the relationship between electric field and potential, and another is the concept of equipotential surfaces. Both concepts are very important, and let us see them one by one. So we are continuing with physics, and we have to see the relationship between, in fact we will derive this relationship between electric field you know is a vector quantity, and electric potential. And electric potential, as you know, is a scalar quantity denoted as V. So if we see carefully, what we can do here is some important points. Suppose this is the direction of electric field. If we keep a positive charge Q in this electric field, this is uniform electric field. I told you uniform electric field means parallel and equally spaced lines. Uniform electric field is parallel and equally spaced lines. So this is a uniform electric field E, and in this uniform electric field E, you have kept a positive charge Q. Then it means you know that this positive charge Q will move in the direction of the field. So a positive charge moves in the direction of the field. So let me write this. A positive charge moves in the direction of field. What is the reason? The reason is electric fields are coming. It means there what type of charge is there? Positive charge is there, because the positive charge will emanate electric field lines away from it, whereas the negative charge will basically electric field will go towards the negative charge. So it means there some positive charge is there, and if there positive charge is there, it means this positive charge would get repelled because of that positive charge. So that is the reason. Whereas a negative charge, if there is a negative charge, suppose you are keeping a negative charge here, minus Q, then the negative charge will move in this direction. Negative charge will move in the direction against that of the electric field. So I am writing a negative charge moves against the direction of electric field. A positive charge moves in the direction of electric field, and a negative charge moves against the direction of the electric field. I hope this concept is clear to you. Apart from this, suppose let us say here a charge Q is there. Let us say I am writing 3 points: point P, point Q, point R. Let us say this is 1 meter, this is 2 meters, and point R is 3 meters. So here if I have to write the electric field at point P, so electric field will be what? Due to the positive charge, electric field will be what? In this direction. This is the direction of the electric field. Basically electric field will be in all the directions in 360 degrees away from the positive charge, but I am just considering this direction. So this is the direction of electric field as far as this point charge Q is. This is a point charge Q. Here a charge Q is there, and these are 3 points: point P, point Q, point R. Now what is the potential at point P? What is the formula of the potential? KQ by R. Formula of potential is what? KQ by R. This is the formula of potential. And what is the formula of electric field? KQ by R square, and it is a vector quantity. Formula of potential is KQ by R. So what is the potential at point P? KQ by 1. Potential at point P is KQ by 1. What is the potential at point Q? KQ by 2. And what is the potential at point R? KQ by 3. This distance is how much? 3. KQ by 3. So if you see carefully, potential at point P is KQ by 1, potential at point Q is KQ by 2, and potential at point R is KQ by 3. and this is the direction of your electric field. It means one thing is very much clear here, that as you are moving in the direction of the electric field, the potential is decreasing because the denominator is increasing. See carefully here, the denominator is increasing, so this overall magnitude will be reducing. So I can say one thing very much clearly, that as we are moving in the direction of the electric field, the potential decreases. So I am writing that potential decreases in the direction of electric field. Potential decreases in the direction of electric field. Potential decreases in the direction of electric field. This is the important part. I hope this point is clear to you. Potential is decreasing in the direction of electric field. Now let us find the relationship between E and V. We are finding the relationship between E and V. So let me do one thing. Let me take cases. Case 1. I am taking is uniform electric field. Uniform electric field. What am I doing? Basically I am establishing the relationship between electric field and electric potential. So from my illustration, what I have understood is that potential is decreasing in the direction of electric field, because this is the direction of the electric field because of this positive charge Q. 3 points are there, P, Q and R. At point P, potential is KQ by 1. At point Q, it is KQ by 2. And at point R, it is KQ by 3. So as the denominator is increasing, overall fraction would reduce. So potential decreases in the direction of field. This is the concept we have got from our illustration. And now I am deriving the relationship. This relationship I got, but this is basically your theoretical relationship. Now let us get some mathematical formula, as far as relation is concerned. So uniform electric field E is there. So let us say this is your uniform electric field E. Let us say this is point 1 and this is point 2, and this distance between point 1 and point 2 is delta R. 2 points are there, point 1 and point 2, and the distance between them is delta R, and you have to take a positive charge Q from point 1 to point 2. You have to take a positive charge Q from point 1 to point 2. So how will I write the potential? Delta V. Delta V, dear students, you know very well what is delta V. Delta V is V2 minus V1. Remember, delta V, final potential minus initial potential. So here the charge has to be taken from point 1 to point 2. So I am writing delta V, final potential at point 2 minus potential at point 1, V2 minus V1. So I told you how to derive this V2 minus V1. This is nothing but work done by an external force. Work done by an external force to take a charge from point 1 to point 2 divided by its magnitude. Potential difference is nothing but V2 minus V1, because that is final minus initial, which is equals to work done by an external force to take a point charge from position 1 to position 2. And if you remember clearly that I gave you a concept that how this work has to be done. The work should be done in such a manner that there is no change in speed of this charge. The charge should be taken infinitesimally slowly. This charge should be taken so slowly that there is no change in kinetic energy of the charge. That is how we have to perform the work. So I am writing an important point. There is no change in kinetic energy. The change in kinetic energy should be how much? 0. Change in kinetic energy should be 0. So if you see carefully now, see, this positive charge is there. You are saying that a positive charge moves in the direction of the field. And this positive charge, if it is kept here, automatically it will move in this direction. Yes or no? Because of what force? Because of the force QE. The positive charge which is kept here will automatically move in this direction because of the force QE. But it should move in that direction. That is our objective also. But it should move very, very slowly, so that there is no change in kinetic energy of the particle. That is the concept actually. For this you can refer my previous video, in that I have explained it elaborately. So what I am going to do here is, since this charge will move in this direction, so I am going to apply a almost equivalent force, but a little less. then this QE in the other direction, and that force would be known as external force. This is electric force. This force is your electrostatic force, electric force because of which charge is moving in this direction, QE. Why it is moving in this direction? Because that is the direction of your uniform electric field. So I am applying a force, external force in the opposite direction, which should be almost equivalent to that, so that the charge moves, but it moves very, very slowly, because two equal and opposite forces will be there. So my external force should be how much? It should be QE, but it should be in the minus QE, because it is applied in the against direction. Now I am writing this W external. So W external, to take the charge from 1 to 2, is nothing but work done is what? F dot ds. So that will be what? Minus QE dot, what is the distance between the two charges? Delta R. Minus QE dot delta R. Minus QE dot delta R. And when I divide it by Q, then what do I get? Minus E dot delta R, which is your delta V. So we got the formula of delta V. Delta V, any potential difference is minus E dot delta R. Minus E dot delta R. We got the formula of potential difference, minus E dot delta R. Observe here, external force is minus QE dot delta R, because F dot dr, this is F external dot dr, this is the distance between them, divided by Q to get the potential difference. So Q se Q cancel, delta V. So we got the relationship, delta V is equals to minus E dot dr, and you can observe here very carefully, here minus sign is there. That is why I said that potential decreases in the direction of field, because if you are moving in the direction of the field, then E and dr will have the same direction, and E and dr having same direction, it means E dr cos 0 and cos 0 is 1. So positive quantity and negative of positive is negative, so delta V will become negative. It means change in potential is decreasing. That's why I am saying potential decreases in the direction of the electric field. I hope the derivation is pretty much clear to you. So that was for uniform electric field. Similarly, I am going to take for non-uniform electric field, and then we will take some problems. So note it down. Okay, so let us continue. Now let us take case 2. So from case 1, we got one thing clear. If E was uniform, so we got delta V is equals to minus E dot, I can write dr. Delta R or dr, anything. If the distance is very, very small, you can write dr. That was case 1. Now let me take case 2, which is basically of your non-uniform electric field. Non-uniform electric field. Electric field is non-uniform. So let us say something like this. Electric field is like this. This is your electric field. So you know electric field at this particular area will be more, intensity will be more, because here the lines are more crowded, and in this area electric field intensity will be less. But in uniform electric field, intensity at every point is same. So that is the meaning here. Again here also, basically suppose 2 points are there, this is point 1, this is point 2, and you are moving in this direction, this is your dr. Actually here E is basically your variable. E is variable. Electric field is non-uniform, so it is variable. It is a function actually. It will not be a constant quantity. So in your work done, because delta V was what? W external 1 to 2 divided by Q. So here I am going to write like this. Work done will be written as F dot dr. F dot dr. Let us say this point is point 1, so let me write its position vector as R1, and this is R2. So R1 to R2 divided by Q. So that will be QE. So Q will come out. So I am writing minus integral E dot dr from R1 to R2 delta V. So that will be my formula for non-uniform electric field. So the moment E is given to me, I will integrate it and substitute the initial position and the final position. Here we don't know now. In the last case that was not required, because we were knowing the value of E itself. It was a constant value. But here E is non-uniform, so some variable function it is. So we have to integrate it. That depends from case to case. So I got the second formula for delta V. I am writing all the formulas here. So delta V is equals to minus E dot dr for uniform, or I can write delta V is equals to integral of minus E dot dr and integrate it from initial position to final position, r1 to r2. That is for uniform, this is for non-uniform. So that is as far as this is concerned. And I can write one more thing here. Basically, if you see here, then what I can write is, see, if you see E, by electric field is what? Is vector quantity. So we can write it like this: Ex I cap plus Ey j cap plus Ez k cap. We can write like this. And your R vector you should know in your physics vectors. That is nothing but your x I cap plus y j cap plus z k cap. So what is going to be your dr vector? Dr vector will be dx I cap plus dy j cap plus dz k cap. Now this is your E vector and this is your dr vector. So if you need to take the dot product between them, E dot dr. So what will be that? There will be this dot this dot this, and this dot this. So I dot I, you know, is what? 1. So I am going to have Ex dx plus Ey dy. Component wise we have to basically multiply them, Ez dz. So that will be my E dot dr. That will be my E dot dr. And if I put a minus sign, minus E dot dr, then that will be what? That will be my delta V. So I am going to write here minus Ex dx minus Ey dy minus Ez dz. Okay. So now this quantity is there now. See this quantity minus Ex dx. This quantity, suppose your x, y is 0, z is 0. Along y and z it is 0. So can I write it like this? Del V. Del V. Del V means partial differentiation. Partial differentiation. Del V. So I will write del V is equals to minus Ex dx. So from here what we write? Ex. Ex will become minus del V by del x. Similarly Ey, what will become? Minus del V by del y. And similarly your Ez. So that is your, if you want to write in the terms of partial derivatives, then you can write like that also. See, this is your E electric field written in terms of vectors, dr written in terms of vector, taken their dot product, and if you put a minus sign, then that is nothing but your delta V. And if suppose you are assuming y and z 0, differentiation you are doing, but if you assume y and z 0, it means you are differentiating only with respect to x. So you are calling that as partial derivatives. So you can write here as del V instead of delta V, del V. That will become minus Ex dx. So Ex will become minus del V by del x. So your electric field E, which you are writing as Ex I cap plus Ey j cap plus Ez k cap, that can be written like this also. What is your Ex? Ex is your minus del V by del x. So you can write like that. Minus del V by del x I cap. Then Ey is what? Minus del V by del y j cap. And what is z? Del V by del z k cap. That way also you can write your electric field. See, observe, understand here. Here you are writing potential in terms of electric field. Here you are writing electric field in terms of potential. That's why I am saying. This is already your relationship between E and V. This is uniform for non-uniform. How will you understand whether the electric field is uniform or non-uniform? If electric field is given a number, for example, it is given 10 newtons per coulomb or 20 newtons per coulomb, it means there is a constant number. So that is your uniform electric field. But if electric field is given as a function of, it may be given as a function of time, it may be given as a function of position. So if it is given as a function of position, suppose electric field is 2 I cap plus 3 j cap plus 4 k cap. Now this is not a uniform electric field. This is a non-uniform. So in that case, what you can write is R1 to R2. You can integrate it like this. So that is the relationship between V and E. V in terms of E. Now here I am writing E in terms of V. So that is as far as your uniform and non-uniform electric field is concerned. So let me do one thing. I am going to take some good conceptual problems on this uniform and non-uniform electric field and how to determine the potentials. And you note it down so that I can move to questions. So let us continue. If you see this question, here there is a uniform electric field 5 into 10 power 3 newtons per coulomb, and a triangle is given A, B, C. This side is your 5 centimeter, this is your 3 centimeter, this is your 90 degrees. So the question asked is here potential difference VB minus VA, next is VC minus VB, and VA minus VC. 3 questions are asked. So let us do them one by one. See, now this is uniform electric field. So now there are 2 methods basically. One, you can directly apply the formula. Formula is this, delta V equals to minus E dot dr. This is the formula. But I would advise you not to use this formula, but rather than go by the concept. And what is the concept? Concept is potential decreases in the direction of field. Potential decreases in the direction of field. If you are moving in the direction of the field, the potential will decrease. So let us use this. So what you have to do here is you calculate the magnitude of E dot dr. Calculate the magnitude of that. You calculate the magnitude of this. Yani you calculate its modulus, and later we will attach sign. For example, let us see first part, VB minus VA, VB minus VA. So let us say this delta V, VB minus VA. Formula is what? Minus E dot dr. You don't do minus E dot dr. What you do is you calculate E dot dr. This is a shortcut I am telling you. This method will get your results faster. So E dot dr. So what is E? 5 into 10 power 3. And what is dr? Between A and B, what is the difference? If this is 5, this is 3, so this will be what? 4 centimeters. So can I write 4 into 10 to the power minus 2 meters, so that I can take everything in SI units. So E dot dr, so simply multiply them. So 5 into 10 power 3 into 4 into 10 power minus 2. So 5 4s are 20 and one more 0. 200. So your delta V is how much? 200. This is the magnitude. Now we need to attach the sign. So what are they asking? VB minus VA. VB minus VA. You are moving in the direction of the electric field. When you are moving in the direction of the electric field, then potential decreases. It means potential of B will be less than potential of A. So they are asking your VB minus VA. They are asking VB minus VA. So potential of B will be smaller than potential of A. So this quantity will be smaller. So smaller minus larger quantity minus 200. And you can write volts, minus 200 volts. Have you understood? Once again observe here. Instead of putting the formula minus E dot dr, you just calculate the magnitude alone. Forget about plus minus. Plus minus we are going to decide from the concept. Potential decreases in the direction of field. So here I have calculated E dot dr. So that is 5 into 10 power 3 into dr. Acha, dot dr. Dot dr means what? Cos 0, because this and this both are in the same direction. So cos 0 is what? 1. So 200 and minus sign. Why? Because they are asking VB minus VA. When you are going in the direction of the field, potential of B will be less than potential of A. So minus. Similarly, let us do VC minus VA. VC minus VA, delta V. So E dot dr. So here if you see between this point and this point. Now if you see this, your dr is perpendicular to your electric field. Electric field and dr direction is making an angle of 90 degree, and you know cos 90 is how much? 0. So potential difference will be 0. So point B and point C are at the same potential. They do not have any potential difference. They are having at the same potential. Let us see VA minus VC. VA minus VC. So if you see carefully, your electric field is in this direction, but your dr vector is in this direction. So what is this angle? We need to know this angle. This angle, let us say, is theta. Okay. So first let us write delta V. Delta V is what? E dot dr, or I can say E dr cos theta. So E is how much? 5 into 10 to the power 3. Dr. This dr is how much? 5 centimeter. Yani 5 into 10 to the power minus 2 into cos theta. Cos theta. Cos theta means base upon hypotenuse. So that will be basically your 4 by 5. So 5 and 5 cancels. So 5 4s are 20 and 200, and again 3 and minus 2 means what? Basically 1. So 20 into 0, volts. That is your delta V. But what are they asking? VA minus VC. They are asking VA minus VC. So you are moving in the direction of the electric field. If you are moving in the direction of the electric field, then potential decreases. It means potential at C will be less than potential at A. It means potential at C is less than potential at A. It means VA is larger than VC. It means the answer is plus 200 volts. I hope it is clear to you. So that was your 3 parts question. So let us move to the next question now. Let us see here question. So electric field here is given 40 volts per meter, and this is uniform electric field. Here a square of side 2 meters is there, and they are asking VB minus VA, VA minus VD, VD minus VC, and VC minus VA. So let us do them one by one, dear students. VB minus VA. So VB minus VA. So if you see carefully, this DR and electric field in the same direction. So E DR cos 0. So E is how much? 40 volts per meter. That is another unit of electric field. 2 units of electric field are there. One is basically newtons per coulomb, and now you know that V is equals to E into R. So E is what? V by R, so which is volts per meter. So that is what they are using. That is the another unit of electric field. So volts per meter is, again you can say, is also SI unit only. So 40 into 2 is how much? 80. So I mean your VB minus VA is 80. Now we need to attach what? Sign. So now when you are moving in the direction of electric field, potential decreases. It means potential at B will be less than potential at A. So my answer is minus 80 volts. I hope it is clear to you. First you calculate the magnitude part alone, which is your EDR cos theta. Here E and DR in the same direction cos 0, 1. So 40 into 2, 80. And then at last apply the sign based on this concept. Potential decreases in the direction of field. So potential at B is small than potential at A because you are moving in the direction of the electric field. So minus. Now VA minus VD. VA minus VD. Now if you see carefully, this DR is perpendicular to the electric field. So DR and electric field perpendicular. It means what? Cos 90, 0. VD minus VC. VD minus VC. This is also 2 meters. Electric field in the same direction. So again 40 into 2. Cos 0 is 1. And VD minus VC. VD minus VC. When you are moving in the direction of the electric field, potential decreases. It means potential at C is smaller. Potential at D is larger. You are asking larger minus smaller. So I am saying plus. Answer is plus 80 volts. Finally VC minus VA. VC minus VA. Yani this is your DR vector. This is your DR vector. And this is your electric field. What is the angle it makes? This angle obviously is 45 degree because this is a square. So my answer is 40 into. This is how much? So if this is 2. If this is 2. This is 2. Then this becomes how much? 2 root 2. 40 into 2 root 2 into cos theta. Cos theta is how much? 1 by root 2. Root 2 cancels. Answer is how much? 80 volts. Plus or minus? You are asking VC minus VA. If you are moving in the direction of the electric field, potential decreases. So potential at C will be smaller. So you are asking smaller minus larger. Answer is minus 80 volts. I hope all the 4 problems are clear to you. Calculate the magnitude part alone as for EDR. Attach sign based on this concept. Potential decreases in the direction of the field. Why I am saying? Otherwise if you use this, then you will have problems in calculating the angle as well as the minus sign, because here vectors knowledge is required, which is basically taken care more elaborately in 12th standard mathematics only. So I gave you a shortcut, and that's the way you can do it. I hope both the problems are clear to you. Let us take up some more problems. Both the problems were on uniform electric field A. Note it down. Okay, so let us see this question. The next question. Here voltage is given x square plus y. We have to find the electric field. Voltage is given, electric field is asked. So if you see carefully, we can write like this. I told you a formula that E can be written as Ex I cap plus Ey j cap plus Ez k cap. Yes or no? And I told you what was Ex. Ex was basically minus del V by del x, and Ey was minus del V by del y. What is the meaning of this? Del V by del x means derivative of V with respect to x, keeping other things constant. Y and Z should be considered as constant. So here we need to find E. So let me do one thing. Let me say that E is equals to Ex I cap plus Ey j cap, because there is no z, so I am not writing the third component. And Ex is what? Minus del v by del x. So minus, what is the derivative of this function with respect to x? So this part is y, its derivative will become 0 because y is supposed to be treated as constant. In partial differentiation, this is the symbol of partial differentiation. When I am saying del v by del x means differentiate with respect to y, differentiate with respect to x, keeping y and z as constant, and derivative of constant is what? 0. So derivative of x square will become 2x. Similarly Ey, that is minus del v by del y. So derivative of x square is 0 because x is constant, so x square is also constant, and derivative of y is 1, so minus 1. So Ex is Ex I cap, any minus 2x I cap plus Ey minus j cap. That is your electric field. You can see here this is a variable non-uniform electric field because it depends on x. As x will keep on changing its value, electric field will keep on changing. Uniform electric field means a constant value. This is a non-uniform electric field. Okay, so that is as far as that question is concerned. Let us see this question. Here electric field is given and they are asking the potential. Electric field E is given, potential is asked. Here V is given, electric field is asked. So we have a relationship delta V is equals to minus integral E dot dr R1 to R2. Yes or no? For non-uniform. Even I can write like this also. Delta V is equals to minus E dot dx. This will be from x1 to x2 minus E dot dy, that will be from y1 to y2, and similarly z1 to z2. See, observe here, this is your E dot dr. Now this I am separating as x and y, so that's why I am writing E dot dx, but then limits of x, and then E dot dy, limits of y. So delta V means what? V2 minus V1. So here they are asking find the potential at x comma y. This is some point x comma y. If potential at origin means what is the point? 0 comma 0 is 5 volts. So final potential which is at x comma y minus initial potential which is 5, delta V. This is I have written delta V. Final potential minus initial potential is equals to minus E dot dx. E dot dx. So 2x I cap dot dx. Dx means what? Basically here di cap. Dx means dx I cap and dy means dy j cap. So 2x dot dx. So that will become what? 2x, integration of 2x from where to where? 0, because x1 is what? 0, and what is x2? x2 is nothing but x dx. Then again minus sign e. So this time I will take the y component. So that is 3y dy. J dot j become 1 and y1 initial point is 0 and final point is what? Again y. So now I can easily write it. V minus 5 is equals to minus integration of this is 2, integration of x is what? X square by 2. And when I substitute the limits 0 and upper limit x, so x minus 0 is x only. So I am getting the same thing, minus 3. You are having y. What is integration of y? Y square by 2. Again 0 to y. So I get the same thing. And so my answer is V is equals to 2 से 2 cancels, minus x square minus 3 y square by 2 plus 5 volts. That is my answer. Initial is 5, so that 5 came here. I hope this is clear to you. Once again, electric field E is given, we have to find the potential. So this is our formula. This again I have made it component wise x and y. So for dx part I am using the x component which is 2x, and for dy part I am using the y component. Initially voltage is 5 volts, initial limits at origin. So for x also 0, for y also 0, final limits. For x it is 1, x only, and for y also it is y only. So we have substituted and we got it. Let us see the third problem. Again here voltage is given and they are asking the electric field. Same way, here also voltage was given, electric field is asked. So here also voltage is given, they are asking the electric field at x equals to 1. So electric field is nothing but Ex I cap, Ey j cap, and Ez k cap. Obviously here y components are not there, so that will not be there. So Ex is only there. And you know Ex is what? Minus del V by del X. So minus del by del X of V. This is your V, which is how much? 5x square plus 10x minus 9. So let us find Ex. So minus came out. Derivative of 5x square is what? 5 into 2x minus 10. Derivative of x is how much? 1. And derivative of constant is 0. This is differentiation you are doing. Now Ex became how much? Minus 10x minus 10. But you need to find where? You need to find at x equals to 1. Electric field E at x equals to 1. So substitute here minus 10 into 1 minus 10. How much you are getting? Minus 20 volts. So this is your voltage, 5x square plus 10x plus 9. You have to find the electric field at x equals to 1. So that is your electric field minus derivative of this. So derivative of 5x square, which is your minus 5 into derivative of x square is 2x, and derivative of 10 is, as it 10x is 10 minus sign outside. At x equals to 1 you are asking. So minus 10x minus 10, substituted x equals to 1, you got minus 20. This option is there, na? This is your minus 20 volts per meter. So I will go with option D, minus 20 volts per meter. Why? Because we are doing volts per meter. That is another unit of electric field. So that is as far as this question is concerned. I hope all the three problems are clear to you. So we have seen problems on both uniform as well as non-uniform electric field, and the concept is quite simple only. Now we are moving to the next concept, which is your equipotential surface. So you can note it down so that we can move to the next concept. Okay, so now let us move to the concept of equipotential surface. Very important concept, equipotential surface. So basically equipotential surface means a surface at every point of which potential is same. A surface at every point of which potential is same. At every point of that surface potential is same. Such surface is known as equipotential surface. Let me explain you through an example. Suppose you are having a positive charge Q. Suppose there is a positive charge Q. Now, suppose here is that positive charge Q. So where are the electric field lines? So electric field lines will be basically away from this. And suppose at, let us say this is at this point. Let us say here at this point, at this distance r. What is the potential? KQ by R. Similarly, I can take a point here. At this distance, what is the potential? Again KQ by R. Let us say this distance is also R. Same, let us say this distance is also R. So at this point, what is the potential? Same KQ by R. So if you make a surface like this, that is your sphere. If you make a sphere, because here also, see, observe here, it's not a circle, it's a sphere. Why? Because at this distance also, suppose you are coming in forward direction at a distance R, here also potential will be what? KQ by R, because potential is not a vector quantity, it's a scalar quantity only. So we have to just see the magnitude only. So here also it is KQ by R. Even if you go behind, here if you keep a point charge at the center of the football, then at every point on the surface of the football, potential will be what? KQ by R, as long as the radius of that football is R. So that surface at every point of which potential is same, potential is equal, that surface is known as what? Equipotential surface. Similarly, you can create one more. Suppose instead of R, you are going to some other R dash. You are going to some other R dash. Some other, there also if you create a sphere, you will get again what? Again you will get one more surface, one more spherical surface at which potential will be same. At this point potential will be what? KQ by R1. here, or KQ by R dash, here also KQ by R dash, here also KQ by R dash. So what I am saying is, for a point charge, concentric spherical surfaces, concentric spheres or concentric spherical surfaces are nothing but your equipotential surfaces, So that is as far as point charge is concerned. Similarly, suppose you want to consider a line charge. Suppose you are having a line charge. Line charge, you remember linear charge density lambda, which was basically your charge distributed per unit length. So here this is your line charge. Then here if you see the potential at this point, because this distance, similarly you can come here also, you can go there also. Similarly at this distance if you see R. So what you are going to get is basically you are going to get a curved surface area like this, curved surface area of the cylinder. Because if this is your linear charge, then if you take here the potential, because this distance will be same, here charge is same, similarly here also distance will be same, here also, what you are going to get, you are going to get a cylinder kind of surface. So that will be your curved surface area of the cylinder. So here the equipotential surface is what? That is CSA of a cylinder. This is infinite line charge, so we are not considering this top surface and bottom surface. It is infinite. Similarly, you can have sheets also. Sheets. Suppose this is your sheet. Here a surface charge density will be there. Already we have discussed in your electric field. Here linear charge density will be there, charge distributed per unit length. Here surface charge density sigma will be there, which is charge distributed per unit area. Now here if you see the potential, then suppose if I take a plane here, like this, if I take a plane, then at that point, since distance is same, so potential will be same, because formula of potential is what? Basically KQ by R. So here it is parallel planes, I can say. Here parallel planes are what? Equipotential surface. So in case of sheet, your parallel planes are equipotential surface. So that is the concept of equipotential surface basically. You have to remember, for a point charge it is sphere, or you can say concentric spheres. But of course, concentric spheres does not mean the potential at this sphere and this sphere is same. No, potential at every point of this sphere is same, and potential at every point of the second sphere is also same, but which is different from the first sphere, because the radius is different now. So for a line charge it is CSA of cylinder, and for a thin sheet it is your equipotential surface is your plane sheets. So that is as far as the concept of equipotential surface is there, a surface at every point of which potential is same. So you note it down, and I am going to give some interesting points about equipotential surface. So note it down. Some important points about equipotential surface. Some important points about equipotential surface. Some important points about equipotential surface. So point number one is that, which is obvious because that is the definition of equipotential surface. At every point of that surface potential is same. So that I will write as point 1 itself, that potential is same. Potential is same at every point. It means that potential difference will be what? 0. There will not be any change in potential difference, because suppose this is that surface. Suppose this is some imaginary surface is there. This is point 1 and this is point 2. So here V1 and V2. So we know V1 is equals to V2. So delta V will be what? 0, because potential is same at both the points, because that is your equipotential surface. So that is point number 1. Let us see point number 2. Point number 2 is that no work is done. No work is done to carry a charge from point 1 to point 2. Suppose you want to carry a charge q, let us say charge q is there, you want to carry from this point to this point, from point 1 to point 2, then you need not do any work, automatically it will go. I mean, no work has to be done. Why? Because we know delta V is W external 1 to 2 divided by q, but delta V is how much? 0. Delta V is 0. As delta V is 0, why? Because that is the equipotential surface. See, no work is done only in case of equipotential surface. If it is not equipotential surface, then obviously there will be a difference of potentials and some work has to be done by external force. So delta V is 0, it means that W external from 1 to 2 is also 0. That is point number 2. Point number 3 is that electric field is always perpendicular to the equipotential surface. That is, E is perpendicular. Electric field E is perpendicular to equipotential surface. Let us try to understand how. See, on a equipotential surface, delta V is how much? 0. And you know what is the relationship between change in potential delta V and electric field? Just now we have learnt delta V is equals to minus E dot dr. If it is a non-uniform, then you can just put an integral sign. Now if you see carefully that for equipotential surface, delta V is 0. For a equipotential surface, delta V is 0. Now if you see carefully, delta V is equals to minus E dot dr. Now electric field is not 0. Electric field will be there, that is not 0, and dr is also not 0. Dr means the distance between point 1 and point 2, that is also not 0. But E dot dr means what? E dr cos theta. So obviously theta should be how much then? 90 degree. Theta should be how much? 90 degree. So if you see carefully, this R is in the direction of equipotential surface, because R is lying on the, suppose this is your equipotential surface, then R is lying like this. So the angle between E and R should be how much? 90, because then only you will get delta V 0. It means electric field is perpendicular to your equipotential surface. That's why I am writing electric field is perpendicular to equipotential surface. I hope that point is clear to you. So E is always perpendicular to equipotential surface, because your cos 90 only will be 0. Point number 3. Point number 4 is that, now if you see carefully, suppose two equipotential surfaces are there. Let us say there are two equipotential surfaces. Okay, so for two equipotential surfaces, suppose these are two equipotential surfaces. This is equipotential surface 1 and this is equipotential surface 2. Now, for this equipotential surface, what is the direction of electric field? This is the direction of electric field. And for this equipotential surface, direction of electric field will be like this, because electric field is always perpendicular to the equipotential surface. Now, we know that already we have learned in properties of electric field lines that two electric field lines can never intersect each other. So if two electric field lines cannot intersect each other, it means that their corresponding surfaces, equipotential surfaces, also cannot intersect each other. Because as two electric field lines, suppose these are two surfaces, now they are intersecting. It means these lines, perpendicular lines, will also intersect, but it is not possible. Why? Because electric field lines will never intersect each other. So since electric field lines are not able to intersect, so equipotential surfaces will also not intersect each other. So I am writing that no two equipotential surfaces intersect each other. So these are the 4 important points. No work is done to carry a charge from one point to another point on a equipotential surface, and electric field is always perpendicular to the equipotential surface. As electric field lines cannot intersect each other, similarly equipotential surfaces also cannot intersect each other. For a point charge, equipotential surface is spherical surface. For a line charge, it is curved surface area of a cylinder, and for a sheet, it is your parallel sheets, equipotential surfaces. So that's it as far as this point is clear. And now I am going to take some questions based on this concept. You can note it down. So let us take up this problem. Question is given here. A point charge is taken through some distance in a circle around a charge q. Point charge is taken through some distance in a circle. I mean, point charge is basically made to move in a circle around a charge q. What will be the work done? So let us say, okay, if you see carefully, let us say this is a circle. Here is your point charge. So let me assume that point charge is q naught. So if point charge is taken through some distance in a circle, so this point charge, let us say it is taken from here to here around a charge q. Now there are two cases. Case 1, two cases will be there. Case 1, let us say that charge q is kept at the center. Charge q is kept at the center, because we don't know whether charge q is at the center or not. Point charge, let us say q naught, is taken through some distance in a circle around a charge q. They are asking what is the work done. Now, because of this charge q, if it is at the center, then this radius will be what? R. So at all the points, potential will be same. So the sphere would behave like what? Like a equipotential surface. And if it is a equipotential surface, then if you bring any charge from one point to another point, then the work done will be how much? 0. So in this case, work done will be 0. That is case 1. But case 2, what I can consider is that suppose your charge is not at the center. Let us say your charge is here, center is here, but charge is here, and this is your q naught. Now this time this surface is not an equipotential surface, because if charge q is here, then the equipotential surface would be its sphere. Try to understand. This sphere is not an equipotential surface for this charge q, because this charge q is not at the center. So this is not an equipotential surface. And if it is not an equipotential surface, then if you are bringing any charge q naught from one point to another point, if you are moving it, taking it through some distance, then you have to do some work. To take a charge from one point to another point, some work has to be done, and that work done upon charge q is known as potential difference. But in case 1, since the charge q is at the center, so this sphere would act as a equipotential surface, but at equipotential surface, potential difference is 0, so no work done. So here work done is 0, and here work done is not 0. That is how I have to answer my options. Let us see the second question. Second question is, we have to calculate the electric potential due to an electric dipole at an equatorial position. You know that what is equatorial position and what is axial position. Already we have done elaborately in electric field. So electric dipole means two equal and opposite charges separated by a small distance 2a, and from there we got the concept of dipole moment. So two charges are there. Let us say here is minus q and here is plus q. That is your electric dipole. Let us say this distance between electric dipole is 2l. So they are asking the electric potential due to an electric dipole at an equatorial position. So this position is equatorial position, this perpendicular bisector. This position is equatorial position, this position is axial position, and this position is equatorial position. So suppose here you are asking what is the potential. So if you see carefully, this distance is how much? L, and this distance is also L. Let us say this distance is some r. So this distance will be how much? Some under root L square plus r square, and this distance is also under root L square plus r square. So because of charge minus q, potential here will be what? Kq upon this distance, and because of this also it will be what? Kq upon that. So magnitude is same for potential. So this point, similarly if you take this point, then here also because of this charge, this distance and this distance is same, magnitude again will be same. If you take this point on the equatorial line, here also this distance and this distance is same, because it is falling on the equatorial line. Equatorial line means your perpendicular bisector. So at every time what you are going to get is potential at this point, at this point, at this point, at all the points, potential will be what? Same. So if potential is same, so and that will be how much basically? Because of this and this, because magnitude is same, but here negative charge, here positive charge. So here potential will be how much? 0, because potential is a scalar quantity. Here also potential 0, here also 0, here also. So at every point potential will be how much? 0. I hope you are understanding. Here is a dipole, this is your equatorial position. At this point, this distance is under root L square plus r square. So if you find the potential due to negative charge, k of minus q upon that distance. Similarly, due to positive charge, k of plus q upon that distance. Since both the distances are same, potential scalar quantity, add both of them, you will get how much? 0. So potential here is 0. At every point on this equatorial position, potential is 0. So my answer is 0. Let us go to the second question, third question. Here there is a positive charge, and we know that for a positive charge, electric field lines will be radially outward. So first let me put the direction. So radially outwards, you know that lines should be symmetric. So if one line is above, one line below, one line here, one line there, and they should be symmetric basically. Whatever you are doing, but it should be always symmetric. So that is your positive charge. So field lines are radially outwards. So point 1 we have done. Now 2 points are taken on this field line. One is point Q, one is point Q. P, another point is Q. They are asking the sign of Vp minus Vq. Vp means potential at point P, and Vq means potential at point Q. So sign of Vp minus Vq. So dear students, I mean, you know that in the direction of the electric field, potential decreases. So when you are moving in the direction of the electric field, potential decreases. It means that potential of P will be more than potential of Q. So Vp minus Vq will be what? Positive. Sign will be positive. So here the answer is 0, here the answer is positive, and here it is 0 or non-zero depending upon where the charge Q is placed. That was your concept of relation between electric field and potential, and then we have seen the concept of surface at every point of which potential is same, and such surface is known as equipotential surface. So with that we wrap up this session of potential, and we will meet in the next session, I mean obviously through this mode only, and that will be again more concepts of potential. Basically we'll take different cases, that is potential due to a ring, then due to a dipole, your spheres, and other cases. So that's it as far as this session is concerned. Keep on watching the videos, and physics, chemistry, maths, every topic by topic we are uploading videos. Subscribe the channel, back up these classes with your school texts and reference materials for JEE and NEET. That's it as far as this session is concerned. Thank you, and that's it.